We're going to work some more on logarithms here. Let's review kind of what we did on that last one because we can never get too much practice. So first we're going to solve for x. So we're going to condense these logarithms. So we know that the sum of the logs is the log of the product. So that's going to be log base 3 of x times x minus 2 is equal to 1. Then we can get out of the logarithm by writing the corresponding exponential. 3 to the first is x times x minus 2. We can go ahead and distribute, so we get 3 is equal to x squared minus 2x. We'll make that equal to 0 on our way to factoring this. We'll factor that to get x minus 3 and x plus 1. So at first glance, it looks like we're going to get 3 and negative 1. But if we look at the originals, we can't plug a negative 1 in there because that would make us take a log of a negative, which is not defined. So negative 1 is extraneous, and our only good solution is x equals 3. Let's try the next one. Now here we have the difference in logarithms. So that's going to be the logarithm base 2 of the quotient x over 2x minus 1 still equal to 1. So now we can write our corresponding exponential. 2 to the first is equal to x over 2x minus 1. We can multiply by that denominator, 2x minus 1. So that's going to make these cancel, but it will hit that 2 over there. So we get 2 times the 2x minus 1 is equal to x. So distributing, we're going to get 4x minus 2 equals x. So if we subtract the x and add the 2, we'll get 3x equals 2, which means that x is 2/3. Now let's make sure that's okay. If we plug in 2/3, that'll still be defined there. 2 times 2/3 is 4/3. 4/3 minus 1 is still positive, so that looks like it's going to be legitimate. Okay, let's try the next one. Now we're going to write the corresponding exponential. 16 to the x is equal to 1/4. We're going to write both sides as powers of 2. So that's 2 to the 4th to the x. And this is 1 over 2 squared, which is 2 to the negative 2. So raising a power to a power makes that 2 to the 4x is equal to 2 to the negative 2. Now we can drop the bases and say 4x is equal to negative 2. And so x is going to be a negative 2/4 or a negative 1/2. Remember, there's no problems with a logarithm being equal to a negative. We just can't take the log of a negative. Okay, next one. Same idea. We got x raised to the negative 3/4 is equal to 1/8. So we look at that x to the negative 3/4, and to solve that, we're going to raise both sides to the reciprocal power. So we're going to raise both sides to the negative 4/3 power. So when you raise a power to a power, you multiply those. That's going to pop that x out all by itself. Now the 1/8 is 1 over 2 to the 3rd, which we can then write as 2 to the negative 3 raised to the negative 4/3 power. And so we can cancel the 3's and get 2 to the negative 4. Am I doing that right? I think that was a negative times a negative will be a positive 4. I think that was right. And 2 to the 4th is 16. There's our answer. Okay, now we're going to write our 27 raised to the negative 2/3 power is equal to x. So x is already by itself, so we just got to figure out what 27 to the negative 2/3 is. 27 is 3 to the 3rd raised to the negative 2/3. We can cancel those 3's and get 3 to the negative 2. That's 1 over 3 to the second, which is 1/9, and that's our x. The next one, we're going to raise 2 to the first, and that's going to equal the inside of our first logarithm, logarithm base 5 of x. We'll do it again. 5 to the second is x, and so that means that x is 25. The next one, remember, we're going to use our properties of exponents in reverse. We know that x to the m times x to the n is x to the m plus n. So going right to left, we can write that as 5 to the second times 5 to the logarithm base 5 of 3. 5 to the second we know is 25, and 5 to the logarithm base 5, these are inverses and will cancel each other out, leaving just 3. And we know that 25 times 3 is 75. And we have it. So on the next one, we have two logarithms, same base, being subtracted. So that means we can get the log of their quotient, 6 divided by 13. But 6 over 13 reduces to 1/3. Now you can do this a couple ways. Maybe we should say set it equal to x and write 3 to the x is equal to 1/3. And then see that 1/3 is 3 to the negative 1. Therefore, our x is going to be negative 1. Alternatively, we could have just recognized that that is 3 to the negative 1, and we would have had 3 log base 3 of 3 to the negative 1. Here we have again a logarithm base 3 and an exponential base 3 cancel each other and leave just the negative 1. Okay? On the next one, we have logarithm base 6 plus a logarithm base 6 of 4 plus a logarithm base 6 of 9. So since they're both the same base, when we add the logarithms, that's the log of their product. So we get 4 times 9 is 36. Then we can do one of two things. So you can, if you recognize that 36 is 6 squared, now we have again a logarithm base 6 of an exponential base 6 is just going to cancel and leave us the exponent. Or we could have, if it's easier, I don't know how it looks best to you, we could set it equal to x and then write our corresponding exponential and then see that the x must be 2. Very good. Let's look at the next screen. So now we're going to use our property of logarithms. So I'm going to do this in many steps, but you're welcome to shorten it up a little bit. So when we have the logarithm of a division, that's going to be the difference in the logarithms. So that's going to be the log of x cubed y to the 5th minus the log of z squared. Now we have the log of a product, so that's going to be the sum of the logs. Log of x to the 3rd plus log of y to the 5th, still minus log of z squared. Now we can bring those exponents in front, and so we'll get 3 log x plus 5 log y minus 2 log z, and that's considered an expansion. We broke it apart into as small pieces as we can. Now we can do that again. Let me change that a little bit. Let's call that x to the 1/2. So now we have the natural log of x to the 1/2. Or let me, actually what I really want to do, let me erase that. Let me disguise that a little bit more. Get the eraser that I want. So let's instead call that the square root of x, which we'll recognize as x to the 1/2. So that's going to be the natural log of x to the 1/2 minus the natural log of y to the 4th, z to the 7th. That's going to be 1/2 natural log x. Now we have minus, and then this product becomes the sum, natural log of y to the 4th plus natural log of z to the 7th. Now we can bring those in front, and if you want, also distribute the negative sign. So we're going to get 1/2 natural log x minus 4 natural log y minus 7 natural log z. There's our expansion. All right, the next one, now we're going to go the other direction. So now we're going to condense these. So now we're going to bring this into an exponent, and likewise for each of those. So that's going to become the natural log of x to the 4th plus the natural log of y to the 3rd minus the natural log of z to the 1/2, which we could also write as the square root of z, right? Z to the 1/2 is the square root of z. Now we have a product, so that's going to be the natural log of, or the sum of the logs is the natural log of the product, x to the 4th times y to the 3rd, and a logarithm minus a logarithm is a single logarithm of a division. So it's going to look like that. Okay, let's see if we can do it with the next one. So we're going to call that the log base 3 of x to the 1/2 minus the log base 3 of y to the 3/4 minus the log base 3 of z to the 5th. So that's going to be the log base 3 of the square root of x. Now with the minus sign there, we can make that a division. So that's going to be the square root of x on top, and the y to the 3/4 is the 4th root of y to the 3rd minus the log base 3 of z to the 5th. Now when you divide this again, let's look at this off to the side, because it's going to be, well, we can do it here. Logarithm base 3 of the square root of x over the 4th root of y cubed divided by the z to the 5th. Now to divide by z to the 5th is to multiply by its reciprocal. So that's going to be the square root of x over the 4th root of y cubed times 1 over z to the 5th. All in that logarithm. Well, what that really is the logarithm base 3 of the square root of x over, here's our 4th root of y cubed times z to the 5th. So notice, when you've done a couple dozen of these, you'll see that you can see the two subtractions end up in the denominator. So those are both being divided. All right, let's try another screen. What did I want to do here? Oops, I didn't mean to make a new screen, so I'm just going to go, here's the one I wanted to get to. Okay, so now we have, in this one, this is just an exercise to make you try to use the properties of logarithms as much as you possibly can. So we're going to say, here's an approximation for the log of 3. We're going to say that's about 0.477. Here's an approximation for the log of 2. It's about 0.301. Now, without using our calculator, can we then approximate these 4 logarithms? So our trick is to try to decompose these logarithms using our properties of logarithms into logs of 2s and logs of 3s. And because our logarithm, remember, is a base 10, breaking it into a something to do with a power of 10 would be effective as well. Let's see what happens. So what I'm hoping we can do is see this is the log of, you can either write it as 2 times 2 or 2 squared, either way. And then we can use our properties of logarithms and say that's the log of 2 plus the log of 2. Now we can say, well, the log of 2 is about 0.301, So that's going to be 0.301 plus 0.301, and that's going to be 0.602. See how the game's played? All right, now when you look at 18, you may have to think a little bit, but that's really 2 times 9, and 9 is either 3 times 3 or 3 squared. So to do it differently than we did the last one, let's think of it as being 2 times 3 squared. Does that make sense? Now, using our properties of logarithms, the log of a product is the sum of the logs. So we're going to get the log of 2 plus the log of 3 squared. Now, the log of 3 to the second, we know is going to be, we can bring that exponent in front. That's 2 times the log of 3. Now we know that the log of 2, we're going to say, is about 0.301. And then the log of 3 is about 0.477. Uh-oh, it's going to be a little tougher multiplication than I had intended. Let's see. If we double 477, see, 2 times 7 is 14, carry the 1. 2 times 7 is another 14, plus the 1 is 15. 2 times 4 is 8, plus 1 is, I think, is 0.954. Now we have to do this arithmetic addition. So the 1 and the 4 make 5. The 0 and 5 make another 5. And the 3 and the 9 make 12. And we got to have 3 places to the right of the decimal. There is our answer. Okay, now the next one is really sneaky, and the one after that even sneakier still. Now 2,000, there's no 3's in there at all, but we can think of this as log of 2 times 1,000. Now this is good because 1,000 is a power of 10, and remember our logarithm is base 10. So we can say 1,000 is 10 to the 3 zeros, 10 to the third. So the log of 2, we're going to say, is about 0.301. And the logarithm base 10 of an exponent base 10, those are going to cancel, and we'll get just 3. And that's going to be 3.301. Pretty slick. Let's try this next one. Now, kind of like what we did a minute ago with 2,000, we can think of this as being the, come on pen, it can be the log of 3/10. And now we got a power of 10 in there, which is good news. So now the log of division is the difference in the logarithms. So now the log of 3 is 0.477. Now here's where it gets dicey. The log of 10, logarithm base 10 of 10 to the first, is just 1. Okay, now this is where it gets scary when we have to do some arithmetic here. So signs are different. We have a -1 and a positive 0.477. We're going to subtract them. Since the bigger one is negative, our answer is going to be negative. So we're going to borrow all the way to there. 7 from 10 is 3. 7 from 9 is 2. 4 from 9 is 5. So there's our answer. It's a -0.523. All right, very good.